All right, hello everyone. Hope that you're having a good day. So I'm going to do a quick summary of chapter 3, which is going to be on energy. All right, so the first new concept will be work. Work is done on an object, and this is defined as the product of the force on that object um, multiplied by the distance in which that object is moved. All right, so if we go over to the whiteboard, all right, work, and let me change this color. All right, work is denoted by W. Don't forget that weight was also denoted by W. So a lot of these letters will be getting reused. All right, so your work is equal to force multiplied times the distance that the object is moved. All right, so work is equal to force times distance. So here are SI units. If you remember, we talked about force. That was equal to mass times acceleration. So let me go over here to the side. Force is equal to mass times acceleration. Our mass was kilograms. Acceleration was meters per second squared, which we also defined as 1 Newton, which Newton is denoted by capital N. So this SI unit can look two different ways depending on how you set up those units. So let's say first we do force, which is kilograms times meters per second squared. And then we do distance. We know distance is the length between 2 points, which is going to be in meters. All right. So if we were to put all of this together, we can combine kilograms and meters second squared into a Newton. And we can just multiply that times the distance in meters to get newtons times meters. All right, this is going to be the simplest form for you to remember for the SI unit for work. All right, force in newtons times the distance in meters. So this is the SI units. All right, so back to the slides. All right, so a Newton times a meter is also called a joule. All right, named after the scientist joule, which is a Newton times a meter. So technically, this has several different forms that you can choose from. Newtons times meters, if that's easier for you to remember, put that. If joules, since it's just one letter, it's easier for you to remember, you can put that. You'll get full credit as long as you put one of these SI units. But please make sure when you are doing any sort of word problem where you're dealing with a lot of math, don't just put the scalar numerical value. Make sure you're putting those SI units because you can lose out on points that way. All right, power. Power is the rate at which work is done. Okay, so power is denoted by P, and it is work divided by time. So let's go back to the whiteboard. And I found out last time that I can just kind of scroll down here to get to a different area. All right, so power denoted by the letter P. And here we're going to use capital P. Last time we talked about momentum, that was lowercase p. So make sure you guys are trying to differentiate the fundamental symbols from the SI units and the different fundamental symbols that they share letters, which ones are capitalized, which ones are lowercase, um, just to cut down on confusion. So power is equal to work divided by time. All right, that's supposed to be 2 humps, not 3. Go back. Time. You will get credit for those. All right, back to the slides. So again, joules over seconds, or you can put newtons times meters over seconds. This is also called a watt. So if you ever looked at an electricity bill, so things that keep your lights and your AC running, it's usually measured in watts. All right. The symbol for watts is just capital W. Sometimes you're billed in kilowatt hours. So that's like how much power you used over that billing cycle. All right, so this is what the power companies use to see how much you're using per month. All right, so SI units, either newtons times meters over seconds, or joules over seconds, or watts. I know this is a lot of stuff to memorize. I would just suggest picking one and sticking with it instead of trying to memorize everything. But to each its own, or his or her own. Next slide talks about energy. And energy is defined as the ability to do work, which makes sense. The more energy you have, the more work you are able to do. The less energy you have, the less work you're able to do. Energy that an object has due to its position, that's what we call potential energy. Okay. And potential energy, again, it's due to its position as a result of the gravitational attraction from that position or height. So our gravitational potential energy is weight or mass times gravity times height. So let me write that out for you so you can see what it looks like. Oh, it's down here at the bottom. Potential energy, PE, is equal to mass, lowercase m, times gravity, lowercase g, times height, lowercase h. All right, and the SI units for energy is joules. All right. All right, next we're going to talk about kinetic energy. Kinetic energy is denoted as KE. All right, and it is the work done by an object that is in motion. So it's the work of the moving object. All right, so kinetic energy, KE, is equal to 1/2 mass times velocity squared, or 1/2 mv to the second power. In this equation, you are only squaring the velocity, not the entire equation, or you will get the wrong answer. So again, please, when you're dealing with the word problems, only square velocity. All right, so just like potential energy, kinetic energy is measured in joules. All right, so the SI unit for both kinetic energy, potential energy, that is in joules. Work is in joules as well. So this is 3 concepts: work, kinetic energy, potential energy, that have the same SI units in joules. So there's different forms of energy. We have mechanical, chemical, radiant, electrical, and nuclear. So your mechanical energy, all right, so these are familiar objects and machines that we see in everyday life, like cars, water behind dams, the spinning blades of a steam turbine. All right, so that's mechanical energy. All right, chemical energy involves the chemical reaction known as oxidation. So chemical energy, an example of that would be wood that has been set on fire, and it is undergoing rapid oxidation. All right, so it changes the form of that object. Radiant energy, this travels through space. So these are your microwaves, your infrared waves. 4 is electrical energy. So it's the energy from electromagnetic interactions. So your car batteries, your flashlights, things of that nature. And then the last one, which we'll talk about in chapter 13 further down in the semester, will be nuclear energy. All right, so that's the energy from the atom that involves the nucleus. All right, so nuclear energy, if you think about the sun or nuclear power plants, they use the fusion or splitting of nuclei to get its power. All right, the law of conservation of energy. All right, it states that energy is neither created nor destroyed, only conserved. So energy can be converted from one form to another, but the total energy remains constant. The energy sources of today that we're trying to move away from, petroleum, coal, natural gas, these are known as our fossil fuels. So we're trying to kind of wane off of the dependence of oil, which is what we're primarily using today, and move on to the energy sources of the future, which are more sustainable for future generations. So solar energy, wind energy, biomass, geothermal, and hydrogen energy, these are some of the up and coming energy sources that you will be hearing more of over the next couple of years. So solar energy, we use, if you've ever seen solar panels on top of a house, it utilizes the sunlight and turns it into, electrical energy that can be used within the household. Wind energy uses wind turbines. Biomass energy, this is materials that can be burned and used as fuel. Geothermal, these are natural energy sources like hot springs and things of that nature. Hydrogen is known as one of the lightest and simplest of all the elements, occurring as a diatomic gas, and that can also be used as fuel to release heat. So that can be used as well, and more future research going into that, and new ways of using it will be coming out pretty soon. All right, so that is the gist of chapter 3.